Check. Check. Check.
Good morning, everyone. I welcome you all for the 10th discussion of Student-Scientist Interaction Program organized by B.V. Jagadish Science Center and the National College, Jainagar. The objective of this program is to promote the involvement of students and teachers in scientific research activities, thereby understand the role of scientific attitude in building their personality. In the view of improving the quality of education, it is felt necessary to introduce socio-scientific dialogue amongst the public, that is you all, and the scientists. B.V. Jagadish Science Center proposes to conduct such programs in schools and colleges throughout the state. The topic for today is about the importance of recent picture of our galaxy's supermassive black hole, Sagittarius A star. Now, this image, which is also there on our poster, was revealed on May 12th, just 2 weeks ago. In the next 2 hours, we'll try to understand from today's speaker what is the image about, how does it become important in the understanding of our universe. To carry out this discussion, we have Dr. Sanved Kolekar, Assistant Professor of Indian Institute of Astrophysics. We also have with us Dr. Y.C. Kamala Ma'am, Principal of the National College, Jainagar. On behalf of B.V. Jagadish Science Center and all the student volunteers, I welcome both of you for today's program. Ma'am, I now request you to speak a few words about the event and introduce today's guest to the audience.
Good morning, everybody. Good morning.
Good morning, ma'am.
Yes, now we can start. Dear friends, today we have all assembled here for a very interesting program. On one side, interesting program, and on other side, it is the cutting edge science that it is going on. You are all lucky because you are getting the information, you are getting the analysis about the frontline science at your doorstep, that is in your own college. In that way, you are lucky. Not only you, all the students of National College, whether it is Basavanagudi or Jainagar. We have seen that all of you have assembled. Most of the students are BSc students here. They are all BSc Physics students. So this is the, in a nutshell, this is the importance of the program. As she said, recently a photograph of a black hole in the heart of Milky Way galaxy was revealed. What is its importance? How it is important to us is the central issue. That is what you have to know. Scientists will be knowing. As youngsters, you need to know why it is important, why it is talked about a lot. Knowing about the universe, knowing about the galaxies, about the black hole or a star or a planet is knowing about us. Because we are part of this universe. We are not separated from the universe. So from a star, we have a planetary system. From the planetary system, we have all evolved as human beings. We are all special properties of matter. We are made up of the same matter. The same elements that are present on Earth, that is present in star. 90 plus elements that is present in sun is present within us. So, we are continuously knowing about the universe since the ages. Okay, this is, we are one step ahead now. So, nature has plenty of secrets within its own fabric. It reveals one by one. After revealing one secret, a new information is evolved, and then that leads to the next one. That is how we are here at the 21st century. It is the Einstein's theory of relativity that led to many of the discoveries in cosmology and as well as physics. To say about all these, we have with us a very renowned resource person, Mr. Sanved Kolekar. He is currently an assistant professor at the Indian Institute of Astrophysics, Bangalore. It is in Koramangala. You would have all gone to Forum Mall, but you have not seen, many of you would have not seen Indian Institute of Astrophysics. Your interest should be, after going to Forum Mall, at least to visit and just to see in the first few days. Later on, you will develop interest. He has done his PhD from IUCA, Pune, under the supervision of Professor T. Padmanabhan, a well-known name in gravitational physics. IUCA is a well-known institute in India. It is in Pune, a wonderful institute for learning physics. As a student, you can participate in various summer schools and other activities that is conducted in IUCA. If you see their website, you can see they even provide you transportation, they provide you accommodation, and they will also teach you a lot of good physics. His PhD dissertation is on gravitational dynamics and thermodynamics of horizons. Post PhD, he had held various positions at institutes like Kavli Institute of Theoretical Physics, China, University of Nottingham, UK, Centre de Physique Théorique, CNRS, Marseille, France, and DAE, Department of Atomic Energy, Center for Excellence in Basic Sciences, Mumbai. His broad research interests are in the field of gravity, black hole physics, quantum effects in curved space-time, angandra ಏನು ಅಂದರೆ ಒಂದು ಸ್ವಲ್ಪ ಹೊತ್ತು ಕಾಯಬೇಕು, quantum effects in curved space-time, etc. Some of his current research topics can be broadly classified as black hole physics and quantum information, black hole physics beyond general theory of relativity, analytic probes for investigating the Davis-Unruh effect, and emergent gravity paradigm and quantum gravity. It appears to you so difficult, but I am sure Mr. Dr. Sanved Kolekar will, in few minutes, he will reveal all these subjects such that you will enjoy that. Mr. Sanved Kolekar, of course, has published lots of papers at national and international journals. He has been awarded quite a good number of prizes. The most important ones are, he is been presented SRS award by SSIP India in 2020. He was the leader of Indian delegation on International Olympiad on Astronomy and Astrophysics held in Hungary in 2019. He was one of the participants in the meeting held in Japan along with Nobel laureates in 2011. These are the few he has mentioned, but I am sure there is a lot more in his detailed CV. Dr. Sanved Kolekar, when we requested him to deliver a lecture, he was very happy to accept our invitation and to be present here today. Sir, it is our pleasure to have you here. On behalf of National Education Society, B.B. Jagdish Science Center, National College, Jayanagar, and on behalf of all of you, I extend a warm welcome to you, sir. Today we have with us two distinguished personalities. Dr. Bilikere Dwarkanath, who was senior scientist at DRDO. Not only that, he was an alumni of National College, Jayanagar. Sir, it's our pleasure to welcome you for this program. You are the inspiration for our students. Okay. We also have with us Dr. Suresh, MS. He is a chemist, he is a physicist. He is also an electronics and communication specialist. He was a scientist at ISRO, and after the retirement from ISRO, he joined B&M Institute of Technology as the principal, and now he is doing quite a lot of work for science communication, in the field of science communication. Sir, We welcome you on behalf of all the organizations. It is our pleasure to have you here. We have with us Mr. Altaf, Scientific Officer of BV Jagdish Science Center. Altaf and his team, Ajit and all the other team members. It's my pleasure to welcome you officially for this program. And we have Professor Chelvappa, Head of the Department of Electronics, who will be working for you inside the college as far as these programs are considered. Professor Chelvappa, it's our pleasure to welcome you for this program. The program is for you. Definitely it is for you and only for you, to update you what is happening in this world. So you are all welcome for this program. With this brief welcome speech, I conclude my talk. Thank you.
Thank you, ma'am. On behalf of all of us, we welcome you to the session. Now, I request Dr. Sanved Kolekar, sir, to continue with his discussion.
have another adapter, we can try that too. No, the adapter is not a problem. Just try disconnecting and connecting it once. ಇಲ್ಲ ಇದು ಇದಾಗ್ತಿಲ್ಲ, ಸಪೋರ್ಟ್ ಮಾಡ್ತಿಲ್ಲ. ಲಿಂಕ್ ಆಯ್ತು ಅಂದರೆ ಇದಾಗ್ತಿದೆ ಅಂತ ಹೇಳಿ ತಗೊಳ್ಳಲ್ಲ. ಹಾಂ ತಗೊಂಡು no, now it has again started. ಆಗ್ತಿಲ್ಲ ಹೋಗಿ ಕೊಡೋಕೆ ಹೇಳಿ.
ಅಜಿತ್ ಶೇರ್ ಮಾಡು. ಇಟ್ಸ್ ಬ್ಲಿಂಕಿಂಗ್ ಅಗೇನ್.
Is it any other way? We could, someone else's laptop I can transfer this, someone has MacBook here.
ಮ್ಯಾಕ್ ಇದೆಯಾ ನಮ್ಮ ಹತ್ರ? Check here on the weather. Have pen drive? pen drive ತಗೊಂಬಾ ಅಜಿತ್.
ಅದು ಔಟ್ಪುಟ್ ಎಷ್ಟು ಹರ್ಡ್ಸ್ ಅಂತ ಇದಕ್ಕೆ ಗೊತ್ತಾಗ್ತಿಲ್ಲ, ಅದಕ್ಕೆ ಪ್ರಾಬ್ಲಮ್.
ಬಿಡಿ ಈಗ ಹೋಗಿದ್ದು ಪೆನ್ ಡ್ರೈವ್ ಹೇಳಿ.
ಹಾಂ ಇನ್ಶೂರೆನ್ಸಸ್ ಎಲ್ಲಿ ಬರುತ್ತೆ?
ಜಾಗ ಬಿಡು.
ವಿಂಡೋ ಓಕೆ.
ಪೆನ್ ಡ್ರೈವ್ ಬೇಕಾ ನಿಮಗೆ?
ಡಿಸ್ಪ್ಲೇಸ್ ಓಕೆ. HDMI ಇದೆ, HDMI TV, ಒಂದು ಮಿರರ್ ಅಂತ ಬರ್ತದೆ. ಹೆಂಗೆ ತಗೊಳ್ಳೋದು?
1080pನೇ ಇದೆ.
ಅಜಿತ್ ಹಾಕ್ಬಿಡು, ಪೆನ್ ಡ್ರೈವ್ ಹಾಕ್ಬಿಡು ಇದಕ್ಕೆ.
120 ಸಾರಿ 1080p. ಬರ್ತಿಲ್ಲ, ಅದೇ
ಅಜಿತ್
ತಗೊಳ್ತಿಲ್ಲ.
ಟೈಮ್ ಇಲ್ಲ ಈಗ, ಕ್ಲೋಸ್ ಮಾಡು. ಕ್ಲೋಸ್ ಮಾಡು. ಈ ಪೆನ್ ಡ್ರೈವಲ್ಲಿ ಇರೋದು ಹಾಕ್ಬಿಡು.
ಒಂದು ನಿಮಿಷ ಇರಿ, ಮಾಡ್ತೀನಿ.
ಪೆನ್ ಡ್ರೈವ್ ಹಾಕ್ಬಿಡು. ಇದ್ರ ಕನೆಕ್ಷನ್ ಕೊಡೋಕ್ಕೆ ಹೇಳು ಹೋಗ್ಬಿಟ್ಟು. ಇದು ಚೇಂಜರ್, ಸ್ಲೈಡ್ ಚೇಂಜರ್ ಎಲ್ಲ ಹಾಕಿದ್ಯಾ?
ಕನೆಕ್ಟ್ ಆಗಿದೆ.
ಶೇರ್ ಮಾಡಿ. ಪೆನ್ ಡ್ರೈವ್ ಆನ್ ಆಯಿತು.
You can maybe copy it to your machine.
ಯಾ, ಕಾಪಿ ಮಾಡಿಬಿಡು. ಇದು ಕಾಲರ್ ಮೈಕ್
ಕೊಟ್ಟಾಗ ಅಲ್ಲಿ ಕಾಲರ್ ಆಗಿದೆ ತಗೊಂಬ. ಚೇಂಜ್ ಮಾಡಬೇಕಾಗಿದೆ 2 ಮಿನಿಟ್ಸ್. ಇದು ಕಾಪಿ ಮಾಡಿ ಒಂದ್ಸಲ, ನಾನು ಚೇಂಜ್ ಮಾಡಿ.
ಪಾಸ್ವರ್ಡ್ ಏನು?
You were asking about hertz.
ಅಜಿತ್
60 ಹರ್ಟ್ಸ್ ಎಲ್ಲ ತಮ್ಮದು 60 ಹರ್ಟ್ಸ್ ಇರಲ್ಲ ಇಲ್ಲಿ 50 ಹರ್ಟ್ಸ್ಗೆ ಚೇಂಜ್ ಮಾಡಿ.
ಹರ್ಟ್ಸ್ ಬಗ್ಗೆ ಕೇಳ್ತಿದ್ಯಲ್ಲ.
50 ಹರ್ಟ್ಸ್
You're asking about hertz.
ನಮ್ದು
ರಿಫ್ರೆಶ್ ರೇಟ್ 60 ಹರ್ಟ್ಸ್ ಇದೆಯಾ?
ನಮ್ಮದು 50 ಇರುತ್ತಪ್ಪ ಇಂಡಿಯಾ.
ಅಲ್ಲ, ಅಲ್ಲಿ ಚೇಂಜ್ ಮಾಡ್ಬೋದು, ಅದಕ್ಕೆ ಚೆಕ್ ಮಾಡ್ತಾ ಇತ್ತು.
ಅಮೆರಿಕಾದ್ದು 60 ಹರ್ಟ್ಸ್.
60 ಹರ್ಟ್ಸಿಗೆ ಕೊಟ್ಟರು ತಗೊಳ್ತಿಲ್ಲ ಅದು. ಯಾರಿಗೂ ಚೇಂಜ್
ಸರಿ ಬಿಡು, ಇದು ಹಾಕ್ಬಿಡು ಈಗ. ಹೋಗಿ ಅಜಿತಿಗೆ ಹೇಳು, ಸ್ಕ್ರೀನ್ ಇದಾಗ್ತಾ ಇದೆ.
Can you just scroll down below and see other?
We'll see here only.
Run this way.
It is running.
Okay. I think this will work. This one.
Yeah. We'll check if slide changing. Yeah, this one.
Down.
I'll keep it in my pocket.
It's better. Change the head.
It's on, right? Yeah. Up, down.
And this is the point center.
Okay. So, thank you very much for having me here, and I would like to thank your principal Kamla madam for that very generous and kind introduction, and also BV Jagdish Science Center, the National College, and the Karnataka Education Society for organizing this wonderful set of ideas where you connect, let's say, people working in the research areas with students. Okay, so we already had a bit of a delay. Sorry about that. There was some issue about projecting from my laptop, but now hope everything works on this machine. So without any delay, let me just begin with my talk. Okay, I know you have been waiting since a long time. Okay, so I'm going to talk about this image which you must have seen in the newspapers since the last quite a few days. Hello? Is it better now? Okay, so first we would like to understand what this image is of. Okay, so you must have heard that this is basically a image of a black hole. So let's start from the very beginning. Okay, we'll try to understand what are these objects called black holes. Okay, what are the features that they show, how are they formed, where do they exist in our universe. Okay, and finally I'll come to the part where how this is connected to this shadow. Okay, so we'll start with what are black holes. So we know about Einstein's, or at least we have heard about Einstein's theory of relativity, where he describes gravity not as a force but as a curvature of space-time. Okay, so the idea is that you have a background, your four basically coordinates. So you have the x, y, z, three spatial dimensions, and on top of that you also have the time dimension. So that sort of forms what we call as the space-time. Okay, just your background. Now, if you have any object, okay, which has mass or energy, then the theory tells you that the mass and energy basically causes the background to be curved. Okay, so how is the force replaced over here? So the curvature basically bends the things which basically move around the central object. Okay, so instead of a force, now the background geometry is curved, so it basically bends things around the object, and hence we have the trajectories which look like they have been acted upon by a force, but actually it's the curvature behind it. Okay, and this is the famous equation, the Einstein field equation. So the left part talks about the geometry. So how the geometry will warp, okay? So how it will expand and contract in certain locations, and it will depend on this particular object over here, which basically contains the mass and energy. Okay, so we need not go into the details of the mathematics, but I just wanted to understand that given a distribution of matter and energy, okay, there is a certain way in which the curvature is described. Okay, so for example, if your matter and geometry are distributed in a spherical manner, okay, then naturally the geometry would also be curved in a spherical manner. Okay, and that curved geometry then dictates the path for whatever which moves on that background geometry. Okay, so how do we first of all get such objects? So basically we need to solve that equations. Okay, so suppose you want to apply the Einstein field equations just to our solar system, right? So our solar system also has a distribution of matter energy with the sun being at the center. So that's like a huge mass. Compared to the planets, the sun is very huge. Okay, it has the most amount of matter and energy associated with it. The next object could be possibly be Jupiter and then Saturn. Okay, but they are still less massive compared to the sun. So the major object that we would look at is the sun. So if you have the sun at the center, the geometry around it is described by what is known as the Schwarzschild solution. Okay, in the name of the person who basically first solved that solution. Okay, so this solution was very curious. Okay, so the solution basically said that if the mass is concentrated in such a way that, let's say, if you try to make it more and more dense, okay, if you try to concentrate the mass of the sun into a more and more dense region, okay, so suppose if you compress the mass of the sun into a radius within 3 kilometers, okay, then it would give rise to an object which we now call as a black hole. Okay, during that time they were basically puzzled whether such a object would even exist. So why it was so puzzling? Because it told you that there is a certain radius, okay, which is around 3 kilometers, beyond which even if you try to send light particles outside, okay, they won't be able to come out. So the gravity becomes so strong that even the fastest moving particle, which we know as light, okay, is not able to escape. Okay, so talking in very layman language, like in your 12th standard, you must have learned about escape velocity, right? The concept of escape velocity, binding energy. So for example, if you would like to send an object in space such that it is no longer bound to the gravitational field of the Earth, right? You must have done this calculation that you need to support it with energy such that the total energy becomes positive. So it's no longer bounded, right? The potential energy is usually negative. So if you supply enough amount of kinetic energy, the total becomes positive. So the object can basically leave the field of the Earth, okay? So you must have heard of this number. It's like somewhere around 11.45 kilometers per second, right? So if you send an object, it basically escapes, okay? So similarly, you can talk about such escape velocities, okay? Even in the case of, let's say, this central system, the central spherically symmetric system, okay? And you can ask what is the escape velocity required, okay? So roughly you can try to understand that this particular surface which I'm talking about, okay? So it's a spherical surface, let's say at the distance of 3 kilometers. If you try to calculate the escape velocity, the calculation will tell you that it goes beyond the speed of light. So that itself tells you that there is no object which can travel faster than the speed of light, right? So that gives you a bound, right? So what it tells you is that then any object which lies within the radius of this around 3 kilometers, especially now I'm talking about the sun, okay, it will never escape the gravitational field of that object, okay? So the binding energy will never be greater than 0 to call it as a free particle, okay? So by this calculation, okay, if you look at this particular formula, so what I told you, the numbers were for the sun. But for a general object, if you use this formula, the radius is determined by this particular number which is given over here. So 2gm by c square, okay? So take any particular object which is heavier than the sun, you just put in the numbers and you can correspond a corresponding radius. So this is also known as the Schwarzschild radius, okay? So that defines what we call as the event horizon, okay? So those are technical terms, but basically you try to understand it in terms of the escape velocity, okay? Now this is a very simple solution, okay? Because the central object is defined only in terms of the mass, okay? But suppose what happens if I add some electric charge to it, okay? Suppose I also add some charge total Q, okay, to this particular object. Now according to Newton's gravity, it's only the mass which basically describes the gravitational field outside, right? But in GR, like I said, it is the mass and also energy, right? So once you put a charge, you will have an electric field. So the electric field also has some energy. So that energy also basically warps the background space-time. It also makes it curved. So in Einstein's theory, it is not just mass, but also the charge which basically affects the curvature of space-time, okay? So you can see that this particular formula, which was simple in the case when the object was just described by a mass, okay, is changed if you also put charge to it. And on top of it, if you also give a spin to the central object. We know objects in the universe are basically spinning, right? Because they have angular momentum. So you have angular momentum energy, right? Energy corresponding to angular momentum, right? So that energy is also responsible for the background curvature. So all of these effects, they add together in a certain way, and they basically amplify the gravity at a particular point. Okay, so if you are trying to calculate the escape velocity for a particle, for a central object which just has mass, it will give you a certain number. But if you put on charge to it, that escape velocity required will be higher. If you also put spin to it, it will even be higher because the effects keep on adding up. Okay, so that is how basically the theory of gravity in this sense works. Okay, so just as a picture, you can try to imagine it as a well which is created by the central object. Okay, the heavier it is, the higher electric charge or the spinning part, this central well will be deep and deep. Okay, so you can try to imagine that if you try to give some velocity to a particle over here, it will require more amount of energy to basically come out from the well. Okay, and after a certain limit, if your velocity becomes higher than the speed of light, then it is simply not possible to escape from the depths of this well. Okay, because we know that there is nothing which moves faster than the speed of light. All right. Now, this is basically we can look at what is called as the anatomy of the black hole. Okay. So the surface, which I told you, which is like the event horizon, this is basically like a sphere. So now we are back to the simplest case first. Okay, just the central object which has mass, no charge or spin. Okay, for that object you can draw the picture as something like this. So it has a event horizon, and you can draw this surface above which it has escape velocity less than the speed of light, and then there are regions where it is greater than the speed of light. Okay. So once something basically crosses this surface, so if you have something which basically falls in, it is forever doomed. Okay, it can never come out. Okay. And then there is another nice calculation which you can say that once it crosses in, it has to be, it is basically forced to go to this center. Okay, I'll talk about what this center is in a moment, but let's first understand the kinematics, okay, the trajectories. So if you have something which is moving in this direction, it can go out no matter where you want it to go, okay. If you give it sufficient energy, it can go out till infinity, okay. In this direction, that also works, but it doesn't work inside, okay. So inside, even if you try to send it off in this direction, it is basically, it will after some time, it will go certain distance and then basically fall in and reach the center. So from any point inside this region, everything is just doomed to come to the center, okay. And the calculation shows that it takes a finite amount of time to basically fall into the center. So you cannot have an object which, let's say, forever hovers around any point over here, okay. So it is always attracted right to the center, okay. So that is what basically the theory says. Now let me come to this particular center. So if we try to understand what is at the center, okay, if you try to characterize the geometry over here in terms of curvature, okay. So curvature also has some number. So higher that number, higher it is, larger or more it is curved. Smaller the number, less it is curved, okay. So it is defined in terms of number, what we call as the curvature tensor. So that's just a technical term, okay. But if you try to calculate that number diverges at the center, okay. Now normally in our universe, when we try to understand something through physics, having a quantity which is infinite, okay, is not a good quantity, because nothing actually is infinite, okay. It will have some large number, larger compared to something. But if you try to compute this number, it actually goes to infinity, okay, not like a large number. There is literally a mathematical divergence. So here we have a problem, okay. Basically the equations, the field equations which I showed you earlier, Einstein's equations which describe gravity, they basically fail over here, okay. So what we can say at this moment is we can describe the geometry very close to the central object, but not right at this point, because there the equations fail. We would require some different theory to basically understand it. So that is what the solution is telling you, okay. Now note that this solution is basically static, so it is not evolving for the moment, because I just gave you the central object which had some particular mass, and then you just compressed it to that particular radius, okay. So we can ask the question whether this was just a theoretical or a mathematical solution to that equation, whether such objects really existed in our universe. So that was the next job, okay. So then people try to look at what would happen if you had some real objects, and they would try to first form into such objects, okay, which we call as black holes. Now let's try to understand what are the effects around black holes, okay. So you must have heard about this gravitational time dilation effects in gravity, okay. So essentially what it says is, suppose you have this central object, okay, which could be a black hole or even some heavy object like the sun, and if you place clocks one after the other, which are like radially going outwards. So let's say you have a line on which you just keep clocks, okay, which are obviously, let's say, from the same company, from the same brand, so they are running at the same rate when you make it, and after you keep it, you just keep on watching what is the time shown. So suppose they start off with the same time, let's say 12 o'clock, okay, and then you watch them after some time has passed. What you will realize is the clocks are not moving at the same rate, okay. The closer the clock is to that central object, okay, it will be moving slower, okay, compared to the clock which is basically far off. So let's say if they all started at 12 o'clock, by the time that this clock basically shows like 5 o'clock in the evening, this clock which is closer, it will be still at 2 o'clock. Okay? So in that sense, it is slower. So you could imagine what are the consequences that this would have if you, let's say, have a person which is living close to the object black hole and a person who is living over here. Okay? So suppose you have twins, okay, two people of the same age. And if you place one person over here at this radius, and if you place another person at this particular radius, this effect, this gravitational time dilation effect will tell you that the twin who is closer to the black hole, he will age much slower. Okay? And the twin who is basically sitting here, his age rate would be faster compared to that twin. Okay? So let's say if you put them both when they were 10 years at this place and at this place, and you visited them, let's say when this twin was 10 years older, so let's say if this twin was 20 years older, this particular twin would have been just like 12 or 13 years old. Okay? And of course, so you would ask like, how does this rate depend on? So it obviously depends on the central object. If it is more heavier, then you would have this time dilation to be more severe. Okay? And on top of that, if you put charges spin, then this effects would become more and more severe. Okay? So this is basically the time dilation effect. Okay? Now there is a corresponding effect which is like the inverse. Okay? Because we know that time dilation and frequency shift, they are basically related to the inverse of one another, right? Because like what is frequency? It is 1 by, those just scale wise, it is 1 by delta t, right? So the amount that time has passed, if you just invert it, that will give you something like a frequency rate. Okay? So the same effect, if you try to look in terms of frequencies, what it tells you is, suppose you have a photon, okay, which is being emitted or which is being sent very close to the black hole, okay, and you sent it radially outward. So it will have an effect on the frequency of the photon. So suppose the photon was in visible range, okay, something which you could see, let's say yellow light, okay. By the time it reaches this particular radius, the wavelength would have basically increased, okay, since wavelength is inversely related to the frequency, okay. So the wavelength basically increases, okay, so it goes into the radio range, okay. Similarly, if you have something which is like in X-ray, by the time it comes out, it will become visible. So we know X-rays are higher energy compared to visible, right? What is the form for the energy of, let's say, a photon? It is basically h nu, right? H is the Planck's constant, and nu is the frequency of the photon. So it's just a simple formula. So this effect is called as the gravitational redshift, okay? Because the frequencies are basically getting lesser and lesser, or the wavelength is getting longer and longer. So that is what we call as the redshift effect, okay? Similarly, if you do the opposite, if you send some electromagnetic wave or photons inside into the black hole, the opposite will happen. So suppose you send something which is in visible spectrum, okay, visible light, by the time it reaches close to the black hole, it will become X-ray, okay, it will gain energy. Now, physics students can at least try to understand this in some sort of an intuitive way, okay? And how do we do that? We know when you have an object in a gravitational field, even in Newtonian gravity, when you throw something close to that object, you know it gains energy because the potential energy is being converted into kinetic energy, right? So by the time it reaches very close, the kinetic energy would have become much higher, right? So it gains the potential energy when it comes from this side to this side. And the opposite happens when you go outside, right? If you throw something outside, let's say some mass, then the velocity would be lower when it is far off, right? Because some energy has been, kinetic energy has been expended to overcome the potential. Something similar happens with the photon also, right? So if the photon has higher energy, by the time it likes to come out, it has to overcome the gravitational potential. So it has to spend some energy. And basically that causes the decrease in the wavelength. Okay, that is how you can understand this phenomenon. Okay. Now the third effect I have already mentioned before, that which says that if you cross this boundary, okay, the event horizon, it will basically go and hit the singularity. Okay. So let me come to the next effect, which is also called as the Penrose process. So there is an interesting effect. So suppose you want to draw the energy, okay, from a spinning black hole. Okay, so Penrose basically showed that you can do that. What you have to do is, if you throw some object into close to the black hole, and if the black hole is spinning, okay, and through some process, let's say if you split the object into two pieces, okay, let's say that one piece you called as E1 and E2, okay, and let's say one piece basically it comes out, okay, one piece basically falls in. So under some processes it will be possible to have the energy of the object to be larger than what you basically throw in, okay, if the black hole is spinning. So it is possible to basically extract energy from a spinning black hole, and this process is known as the Penrose process, okay. Another interesting property is what is known as the no-hair theorem. So this is a very curious property. So I've been talking about like central objects or black holes which have basically mass, charge, electric charge and angular momentum, right? But let's say in principle, you can form a black hole by using various different constituents, okay? So you can have objects which are different, which have different color, which have different constituents, right? So for example, you can make the central object from a particular gas, okay, or some particular dust which falls in. So the dust has some constituents, right? It has some definite number of protons, neutrons, electrons, right? So that is one case. Now in the other case, you have something completely different, okay? Let's say suppose you throw in chairs, okay? You throw in chairs and you compress them to form a black hole, okay? But chairs now have different constituents compared to that dust which you throw in, right? But the final black hole which forms, it doesn't remember at all like what has gone in. The only thing that it remembers is the total mass, okay, the electric charge and the angular momentum. So this is called as the no hairs, okay. So there are, so this is a funny term, but it has a very nice, interesting conversation. So which will not get into at this moment, but it's just interesting to know that there are only 3 parameters through which you describe a black hole. So you don't know what has gone in. And this also has consequences in what is known as the information loss, okay. So in quantum mechanics, we know that information is preserved, okay. If you have time evolution, the information cannot be lost. So there is a certain theorems which quantum mechanics says has to follow so that information is conserved. But in the case of black holes, there is certain some effects due to which curiously the information can get lost. So I'll mention about this a little later in my talk. Now you must have also heard about this Hawking radiation from black holes, right? So I told you that nothing escapes from the black hole, okay? But there is an interesting calculation which Hawking showed in 1974, that if you try to do quantum mechanics near a black hole, then you can show that black hole emits some kind of radiation, okay? And that radiation is dependent on these parameters of the black hole, okay? And that radiation is known as Hawking radiation, okay? But that's like a quantum effect. So whatever effects which I said before, they did not have quantum mechanics yet into the part. That was just described by Einstein's gravity. But the moment you introduce quantum mechanics, then you start to have very nice and curious effects. So like for example, this Hawking radiation, okay? You can try to understand Hawking radiation with a simple argument, okay? So you know that in vacuum, okay, you can have like virtual particles which are created. Like quantum mechanics says that delta E and delta T, it is being constrained by the Planck relation, right? The uncertainty relation. So you can violate the energy conservation law for a certain time, right? So some of you might have studied the uncertainty relation. So in vacuum, you can suddenly create like particle and antiparticle pairs, okay? And then they again combine and just go into back to the vacuum. So that is what quantum mechanics says. If you try to do that very close to the event horizon, okay, suppose you have vacuum, you have nothing outside. So just from the vacuum, you have a particle and an antiparticle. And suppose one of the particle, let's say, falls into the event horizon. Now there is a problem for the other particle which is left. It has nothing to recombine and form into the vacuum, right? So the other particle which is left, it basically comes out and acts like the Hawking radiation. So that's like the heuristic way of understanding what is the origin for Hawking radiation, okay? Right. So these are the effects of the black hole solutions. Now the next question was, whether such objects basically exist in our universe. Otherwise, what's the point in having such effects, right? We should first try to see whether we can have them in our universe, okay? So, uh, the, uh, in this slide, I would like to point out the contribution of an Indian scientist, Chandrasekhar, who was awarded the Nobel Prize for his work, who basically showed that there is an interesting consequence and it has a relation to black hole. So now let me explain it in the following manner. So let's say if you look inside a star, you know because of gravity, all matter would try to just go to the central point, right? Because gravity is an attractive force. So everything would be attracted towards the center, right? So why doesn't just everything collapse to the center? Because we have obviously pressure, okay? Pressure coming from the virial theorem, right? So if you have anything which is hot, right? You have something which is hot, then it has pressure, temperature, etc., right? So you would have a pressure just because there is a high temperature. And what causes the temperature? So there is this nuclear fusion which basically goes on in the center of core of stars, right? Hydrogen is being converted into helium. The helium is fused into higher elements. So you get higher and higher elements, okay? So that basically generates high amount of energy which basically sustains the temperature in the core of stars, okay? Photons are generated as a process and they basically come out from the surface, and hence we basically see the stars are shining and emitting black body radiation, right? But it is essentially the equilibrium process, the pressure which basically balances gravity, okay? But now what would happen if let's say the pressure decreases for some reason, okay? Let's say much of the hydrogen is already being converted into helium, right? Now there is no like hydrogen left, okay? So then what will form? So the next process should start, right? Helium should combine and form higher elements, right? But suppose there is not enough, so the fusion is dependent on certain parameters, like what is the scattering cross section enough. So such that there are certain conditions which basically tell you that the fusion should happen, right? The pressure should be enough, the temperature should be enough, the scattering processes should be enough. So if that doesn't happen, then gravity basically wins, okay? And the whole structure, it basically just tries to fall in, okay? So it's just a competition between the pressure and the gravity at the center which decides what happens in the evolution, okay? So Chandrasekhar basically computed the equilibrium relation beyond which gravity wins, okay? And he figured out that if you have an object which is around, let's say, 1.4 times the mass of the sun, okay, then gravity will always win, okay, under certain conditions, okay? And this limit is known as the Chandrasekhar limit, okay? So you would have black holes which are basically massive than the 1.4 times mass of the sun, okay? And to prove this, he invoked some quantum mechanics, which is known as the electron degeneracy pressure, etc. But I won't go into the technical details, but you should know this. So the byproducts of such a process are either you would get basically a white dwarf, okay, or basically a neutron star, or when gravity wins, you would basically form a black hole, okay? So in principle, what it tells you is that black holes are formed as a collapse of stars when they basically run out of fusion energy. They cannot run fusion at the center and when gravity wins. So it is possible to have black holes in our universe, okay? Then later people basically modeled things, okay? So people modeled the evolution by solving the Einstein field equations explicitly, and then they showed that there exist solutions, okay? So you start from the star, and then you have evolution from the star after the collapse, such that you would basically you will basically form black holes, okay? So such solutions exist, okay? And then this also gave rise to the interesting question that if black holes form, then you would also have the event horizon with the black hole. But the more problematic thing would be the central singularity, where I told you that everything, like every physics that we know, just basically breaks down, okay? So GR breaks down at the center. So people initially thought that we couldn't have such objects in the universe, hence black holes could not be possible solutions. But because of such solutions, we were led to believe that this could happen. But this solution was for a spherically symmetric collapse. Okay, then perhaps people argued that you would never have perfect spherical symmetry in our universe. Okay, because our universe, there would be always some deviations from spherical symmetry, right? Nothing is like perfectly symmetric. So perhaps this solution doesn't work. Okay, so here is where the theorem by Penrose came in. Okay, for which he was awarded the Nobel Prize in 2020 for his work. So he was one of the awardees. Okay, so he showed that irrespective of whether you have spherical symmetry or you have deviations for spherical symmetry or you have some arbitrary object, okay, if it satisfies certain conditions, that if you try to compress that huge amount of mass within that particular Schwarzschild radius, okay, or if you try to bring in, it will always form a singularity at the center. Okay, so that was his famous theorem from 1965. Okay, and this theorem was very general. Now I would like to point out that there is another Indian scientist which had contribution which led to this theorem. Okay, so there is this famous Rai-Chaudhuri equation. So that equation basically tells you how trajectories of light, trajectories of photons, they basically focus or defocus when you have background geometry. Okay, so because of background geometry, I told you like space is curved, right? So you would imagine that the photon light is bent. Okay, so if you collect, let's say, such rays of light together and try to understand what happens to these rays of light as they propagate through space time. So this is as time flows. So let's say here they come together, then they spread out, etc. So this equation, this phenomena can be described by this equation, which is known as the Rai-Chaudhuri equation. Okay, and this Rai-Chaudhuri equation also plays a crucial role in basically Penrose's theorem. Okay. So there are certain features which are like caustics, but these are too technical things, so I'll just basically skip. And so I would like to just mention in this picture that you can see that, so this is basically the time evolution. Okay, so the time is along the y-axis over here. So if you cut a cross section, you would look at what the matter distribution is at that particular time. Okay, so this is the starting matter distribution, and once the matter basically crosses the event horizon, okay, so the matter, let's say the star, once it crosses its own event horizon, so it is basically falling towards its center. So it will fall towards the center in a very finite time, and then it will hit the basically what we call as the singularity. Okay, so that is the part of this basic theorem. Okay, so these things we can skip. So how do we basically just heuristically define what is a singularity? So see, every object in this world has a world line. Okay, if you plot it as a function of time, it has to exist somewhere, okay, physically in space at some point in time. So that is what we call as a world line. Okay, so if you imagine that here you have the spatial axis x, y, z, and vertically you have the time axis. So at a given time, it must exist somewhere, right? That is how we will describe an object in the universe. But singularities are such objects that beyond which you don't know how to continue. Okay, so everything fails. So that is a heuristic way of understanding what a singularity is. So it's a problem. Now I'll also skip this technical parts. I'll go now to the second part. Okay, so he was awarded the half of the Nobel Prize for his work in theory. Now I'll go back to the observation part. Okay, so theory part, it is okay. He proved that you have anything which is even imperfect, okay, non-spherical, it will form a black hole. If it satisfies the Chandrasekhar limit, etc., you will have the singularity. Okay, but can we observe it? So that was the work done by Genzel and Guess. Okay, so they essentially looked at the center of our galaxy. Okay, so obviously we don't see this picture nowadays from any city because of light pollution, but if you go to a very dark area and if you look out into the night, okay, you can basically see this picture. Okay, so IIA has an observatory at Hanle in Ladakh. So if you, let's say, visit that observatory and if you just sit outside, you can basically see this picture with your naked eye. Okay, so that is how our Milky Way galaxy will look like. Okay, and we are basically sitting on one of the spiral arms of the Milky Way. Okay, but in the center, if you try to look, we suspect that there is basically a black hole. Okay, so that is what the, Genzel and Guess were trying to see. Okay, so they kind of use some optics to basically see inside. So I'll come to that. So if you try to look at the center, okay, you see a very fuzzy area. So now we are looking right into the center. You can see that there is a lot of dust and other parts which basically come in. So you try to resolve it. Okay, so you're trying to look at a very small part inside. So just to give you an idea of the scale, it's like if you put an apple or a donut on the moon, and you are trying to look at it from here. That's the kind of resolution you would like to have to look at right into the center. Okay, so if you try to look at and if you use adaptive optics, okay, so what adaptive optics basically does is you have a laser along with your telescope which is on the ground. You just shine it at some particular height above the earth and you create a virtual object, okay, by shining the light and heating the object over here. And those light rays, when it basically comes down because of the Earth's atmosphere, the wavefront gets distorted. So the wavefront is ideally like a spherical wavefront, right? But because of the distortions in the atmosphere, okay, the shape of the wavefront it changes, okay. So it's not spherical by the time it comes to your mirror. But because you have created this virtual object and you know everything about it because you have created it, okay, you basically use that information to deform parts of the mirror over here and you correct it and make it again spherical, of the spherical form, okay. Because of this, when you then look out into the sky, things look quite nice. So this picture basically tells you. So this is without that laser or the adaptive optics off. This is the fuzzy picture, but once you turn it on, you can actually see the stars right in the center of the galaxy. Okay, remember this resolution is equivalent to looking like an apple which is kept on the surface of the moon from Earth. Okay, so that is the kind of resolution that we are looking at. And obviously you need to look at in some particular band. So they chose basically this near infrared band because that is where this objects would be basically visible. Now I'll show you this movie. So I want to first you to have a look at this movie and then explain what are the parts in it. So this is essentially a time-lapse picture, okay. The number here basically tells you the year in which this picture were taken, okay. So this is basically 2015, 2016, okay. So this is basically a time-lapse picture of the stars which are basically orbiting somewhere around the center. So we can't see the center exactly. Okay, if it is a black hole, we know it's going to be quite dark, right? So we can only see the stars which move around due to the influence of the gravity of the black hole. So let me run that again. Now, Newton's gravity, okay, it tells you how the orbits around the central object should look like. Like for example, in our solar system, we know that planets, they follow ellipses, right? Circular orbit is a very special orbit. The most general solution for planets, okay, is basically ellipses. So from this picture, can you see clearly an ellipse? Okay, so just from Newton's gravity, we know that roughly it's an ellipse. But when you put in Einstein's gravity, obviously the ellipse is corrected. It's no longer perfectly an ellipse. Okay, there are certain deviations, and that deviations you can compute precisely. So even though it looks like an ellipse, if you look at it in very detail, there will be some corrections due to Einstein's gravity, which you can compute, okay, from this picture. And if you plot that trajectory carefully, you can try to calculate what is the supposedly mass of the object in the center, okay. So what we know is the ellipse has two foci, right? The central object should be sitting on one of the focus, okay. So from the trajectory, you can plot where the focus is, right? So you can guess where the central object lies. So you can compute the mass, right? And you can also compute the distance, okay? So knowing the distance and the mass, you can compute how dense that object is, okay? So that is what they exactly did, okay? So they basically looked at this special star, okay, which is called as the SO2 star. Okay, it has a time period of 16 years, okay, with an eccentricity of 0.88 around the center. Okay, in comparison, our sun is very far from the center of the Milky Way, and it takes about 200 million years to complete one complete revolution around the center of the galaxy. So in that comparison, 200 million years and 16 years, there is a huge difference. Okay, so this star is really, really close to the center. Okay. So what did the computation tell them? The computation tell them that the central object has 4 million times the mass of our sun. Okay. So million means basically 10 lakhs, right? So this is like 40 lakhs. Okay. So if the solar mass is like 10 raised to 30 kg, okay, of the order of 10 raised to 30 kg, you multiply that by 40 lakhs, and that would be the mass of this central object. Okay, and then you can compute what is the distance. Okay, so that distance is equivalent to 125 AU. Okay, so what is 1 AU? 1 AU is roughly the distance between the sun and the earth, right? So 125 times of that. So within that distance, you have such a huge mass sitting over here. Okay, so you can ask whether that mass is concentrated within its corresponding Schwarzschild radius. Okay, so how compact is it? And the answer would be it's a huge mass which is compressed around in a very small region. So what kind of object it is? So you are led to believe that it has to be a black hole, because there is nothing else possible, right? It's a compact, supermassive object. Okay, so for this observations, Genzel and Guess were basically given the other part of the Nobel Prize. Okay, so these are some other interesting figures. Okay, so we need not go into the technical details. So this is roughly the density of the central object, which we see that it's basically huge. So you can see the number over here. So it's 10 raised to 15 in terms of parsecs. Okay, so that's a huge density. Okay. Right, and then in 2015 we had further evidences, okay, whether black holes exist or not. So that was through gravitational waves. Okay, so in general, think about like if you have water, still water, and if you disturb it, then you have waves on that water, right? So similarly, in gravity, since you have the background space-time, if you disturb that space-time, it also create some kind of waves in the space-time. Okay, so those are basically gravitational waves. Okay, so gravitational wave detections in 2015 for the first time basically showed us that there are two black holes which were basically orbiting around each other. They were losing energy and spiraling, and then they basically combined into one central black hole. Okay, and this was observed in the gravitational wave detector. So this was another confirmation that basically black holes do exist in our universe. Okay, so this work was also awarded the Nobel Prize in 2017. Okay, so this itself is a talk in this would be a separate talk, so I don't want to go into the detail. I just wanted to mention that other than the work done by observing the orbits, this was another confirmation that we do have black holes in our universe. Okay. And these are the kind of black holes basically that were found out, but we can skip this. Now, there are other interesting effects of black holes, okay? So now since we have confirmation that they do exist, there are certain quantum effects that black holes show. So I talked about this Hawking radiation from black holes, so this is the explicit formula, okay? But it's a very weak effect, okay? So this formula tells you that the temperature, okay, of this Hawking radiation which comes out from the black holes, it is inversely proportional to the mass of the black hole. So the larger the black hole, smaller is the temperature of the radiation. Okay, so roughly like this gives you a scale, right? So if you had a black hole which is comparable to the mass of the sun, okay, then what is the temperature? It is like 10 power minus 8 Kelvin. So it is very hard to detect, but nonetheless, this effect should be taken into account, okay, because that is what the theory tells you. Okay. Now there are further interesting aspects that I told you about this GR equations, right? They talk about the geometry. So it was found that these equations, they have a nice analogy with the equations of thermodynamics, okay? Now thermodynamics and gravity, they are like very different theories, right? Thermodynamics, you basically use to describe macroscopic quantities, right? Let's say a gas or fluids, okay? But gravity is like geometry, but there is an interesting connection between them. So the evolution of the equations of gravity are somehow analogous to the equations or the laws of thermodynamics. So there is this interesting connection between them. Okay, so I just wanted to mention this. Now let's come back to the central theme of basically this talk. Okay, so far we had not seen explicitly what was at the center. Okay, we had only seen the orbits around. Okay, but this picture which we got from the EHT, the Event Horizon Telescope, actually allows us to look at the central black hole. Okay, so now there are certain features and how this is basically created. So I'll try to now explain this part. So this picture was basically taken by this Event Horizon Telescope, which are like observatories which are not a single observatory, but these are observatories which are distributed all over on places of the earth. Okay, they combined, took pictures of the central object, okay, in radio frequency, and then they combined it together, and collectively we get this particular image. Okay, so there are 8 telescopes around the world, so I'll mention them. Okay, so let's look at the what are the features. Okay, so like I have told you, this is like 4 million times massive, the size of the sun, and the size is same as keeping a donut on the moon, right? Yeah, so what about the distance? The distance is, it's around 27,000 light years away from us. So if you sent a light signal now towards the signal, okay, it will take about 27,000 years, light years for the, or years for the light to basically reach the center, okay, and similarly vice versa. So basically the light we are getting from the central object was emitted 27,000 years ago, okay, so that is the light which we observed now, okay, and it's in radio, okay. So even though we are seeing a picture, it is basically the radio waves which have been converted into this picture for us to look at, okay. It's in the radio band, which is like 1.3 millimeter band. So you obviously can't see radio waves, but it has been converted into a optical image just for our benefit, okay. Now this object basically shows you that there is some dark portion inside, okay, and then there is a sort of a ring-like structure outside, okay. Then there are certain bright regions, and then there are certain less bright regions, okay. So how do we basically explain or try to understand what these features are, okay. So yeah, so let's try to just zoom in into the galaxy from where we are, okay. So we are 27,000 light years away, okay. So if you zoom sufficiently enough, so let's say this scale is 500 light years, then the central part would look like this. This is the galactic center. If you zoom still inside, so now the scale is, let's say, 10 light years, the pictures would look like this. So you are starting to see the central region. So this is still in the radio band, okay. If you zoom to 70 light days, okay, so if light takes just 70 days to cross from one side of this picture to other, then the picture would look like this, okay. So you would see the orbit. So this is basically in the infrared band, okay. If you zoom to 3 light minutes, okay, so if light takes just 3 minutes to go from this side to that side, then that is the scale of the black hole that you are looking at, okay. So it's such a small compact object, okay. By comparison, light takes about 8.5 minutes to reach us from the sun, right? And this is just 3 minutes. So you can imagine how small the central object or the central black hole is, okay. So this is a nice zoom in view of the same thing which I mentioned. So this is in the radio light. So now we are basically resolving it, right? So we are looking at the center and we are trying to magnify the inside region more and more, okay. So this is how powerful our current telescopes are, okay. So that's the central object. Okay. It is also equivalent to, like, say, suppose you are sitting in Kanyakumari and somebody has opened a newspaper in Delhi. Okay, then you can sit in Kanyakumari and read the newspaper in Delhi. So that is the resolution which we are seeing here. Okay, to give you a size of that object, this whole object can basically fit inside the orbit of Mercury around Sun. Okay, but remember what the mass was. It was 40 lakhs times the mass of the Sun. Okay, so it is massive, but yet very compact. Okay, just to give you a feel of the scale. Yeah. So now let's try to understand how the image is formed. Okay. So basically, the theory of gravity tells you that because of the space-time curvature, if you have, let's say, light traveling, okay, because of gravity, it will be basically bent. Okay. So suppose it follows this path. It comes towards this star, so which is the Sun. Because of Sun's gravity, the path is bent. Okay. So it turns over here, and then it reaches you at Earth. Okay. So you would see the star. So if you extend this ray back, okay, this will be the apparent position of the star. Okay. You would see from Earth. You will not see it over there, but you will see it here in the background of other stars. Okay. Now obviously the Earth moves around the Sun, right? So you know what the actual position of the star is, because when the Earth, let's say, goes there, you can observe this star which is in a given background. Now there is no Sun in between. But if you come to this side, when the Sun is between that star and if you observe it, then the path would be bent. So this star would be appearing in some different background of star. So that's how you figure out that the star has moved. In fact, this was the experiment that Eddington did in 1999 to verify that Einstein's theory of general relativity was correct. Okay. So this can be done during a solar eclipse, because what happens is you get huge amount of light from the Sun, right? So you obviously cannot see the star. You see the star during the night time. So how do you see something which is behind the Sun during the day? So you need something to block this. So it can be done only during a solar eclipse. When the moon is between, it is blocking the light from the Sun. Okay, the star which is just beyond that particular disk would be basically visible, and that is what basically Eddington did, and he verified. So what did he verify? So there is this bending angle, right? So there is this angle theta, which can be computed using that theory. So there is a particular formula. So what he observed was basically precisely that angle. Okay. Now actually the calculation or the observation he did, there was a lot of noise, so the error was quite big. Okay. But later many people redid that calculation later, and then Einstein's theory was correct precisely, okay, to very small numbers. Okay. So that is how this was verified. Now what I showed you is just slight bending, okay, even though it is exaggerated in this picture. Okay. There are other cases where you can see the bending of light. Okay. So for example, if you look out into the sky, you can see clusters of galaxies, okay, galaxy clusters. So galaxies which are like closer to each other. And let's say if you have an object which is away or behind this cluster of galaxies, okay, and this object, which is again could be a bright galaxy which is emitting some light, this light, when it actually travels around this direction, because of this curvature created due to this distribution of matter and energy due to these galaxies, it will basically bend, right? So by the time it reaches us in our telescope, you will be getting the light from this background galaxy through different paths. So there is one path which comes in this direction, and then there is another path which comes through this direction. So it is the same object of which you are seeing multiple images. Okay. So how do you know it's the same object? You can study the spectral image of that object. Right, the spectral image, when you study the lines emitted by this object, it can tell you that it's the same image. Okay, so there are ways to check it. So if you do that, you find that this has the same spectrum as this object, as the same spectrum, it is exactly the same. So it is the same object which you are seeing, but you are seeing multiple images due to the lensing. Okay, so you can imagine that in place of this cluster of galaxies, suppose you just put a lens. In optics, you must have done that experiment, right? Just put a lens in between and have an object behind the lens, and then it is basically focused by that lens, and you see the image somewhere here. So it is the same, the mathematics is kind of same, okay? You can replace this masses or the curvature geometry over here by just a lens. Okay, you can understand it in the same way, and you will see the image which is focused in this plane over here. So this is the plane of your telescope. Okay, so this lensing is quite severe compared to this small lensing which we observed due to the sun. Okay. Now, in the case of black hole, the gravitation lensing is so severe that suppose you had a light ray which is coming towards the black hole, then it can be either captured by the black hole, okay, it can directly go in, okay, or it can just go continuously around a circle around the black hole, okay. The gravity is so strong, or the curvature is so strong, that there is a place around the black hole which is known as the photon sphere or the photon ring, such that light can go on a circular orbit around the black hole. Okay, so that is known as the photon ring. Okay, this is the event horizon. Okay, which we talked about. So beyond, if something falls in, it can never escape out. So this is that boundary, and a little away from that sphere we have another sphere, so which is the photon sphere, around which light can go around in perfect circles. Okay, so this is the same picture which I am showing you. So suppose there is light which is basically coming in, okay, so it is bent towards the black hole, and if it is following this particular trajectory, then it can lie forever on this particular photon sphere, which is the dotted outside dotted line, and if it goes inside the dotted line, then it has to basically fall into the event horizon. Okay, so this is like a second boundary. If light crosses this outer boundary, okay, then it has to cross the event horizon eventually. Okay, so that is the photon ring. But note, it is different than the event horizon. Okay, in event horizon, if you send something radially outward, it cannot come out. But in between this region, which is the event horizon and the photon ring, if you send something radially outward, it can come out. Okay, it is just that rays which are not radial falling inside, but which are tangential, okay, they have to fall inside. Okay, so you can have different type of rays, okay, which basically go along this orbit at this particular photon ring and always stay there, or you can have orbits which basically fall inside the event horizon. Okay, so now this is basically what is happening. So you have certain light rays which is emitted by the background object. Okay, so let's say you follow this ray, the blue ray. The blue ray is bent around and it reaches our eye over here. So you trace it back. So the object will look like this to us. Okay, it will be present at this position. Now there will be other rays which will be coming from the background object, which will basically complete one complete revolution along the black hole, and then it will reach us along this point. So if you extend them, you will get an image present over here. Okay, and similarly there were other rays which will complete 2 revolutions, then 3 revolutions. So you will get them at different locations. So if you trace them, you will not get everything at a single point, but like the multiple images in the previous case, you will get the same picture of the galaxy at different locations. Okay, so the different locations would correspond to how many times that light has basically gone around the black hole in those many number of circles. Okay. Now, when we are trying to look at the black hole at the center of the galaxy, what light we are essentially seeing. Okay, so this is the idea what we have, what happens at the center of the galaxy. So you have that black hole which is sitting here, and then you have sort of gas, okay, which is spiraling around the black hole. Okay, so it's like a disk, and this gas is basically going around the black hole, but there is like friction which happens. Okay, so it's not going around in just like perfect circle orbits. So there is friction among the different components of the gas, so it's losing energy. Hence, it will just continuously spiral inwards, okay, and it falls into the black hole. Certain particles or certain dust or certain type, the particles in the gas, it will also travel along to the north pole or the south pole of the black hole, and there will also be magnetic field lines, okay, because this gas would be at high temperature, so it would be ionized, so there would be magnetic line presence. So if you have like ions traveling in the magnetic field, then you would have synchrotron radiation, etc., right? So those kind of radiation effects which you would have. So you see this kind of jets which come out, okay, and this central disk, and you have the event, you have the black hole at the center. So this is basically the event horizon. Now this picture doesn't take into account gravitational lensing yet, or the bending. This is just the pure picture that we would like to imagine without the bending of light. Okay, so this is where the actual matter would lie at a fixed distance, but this is not the picture that we would see, or this is not the picture as captured by the telescope, okay, because we have not seen yet how the light would bend. So this is just the distribution of matter around matter and gas around the black hole, okay. So this is the picture that actually you would see. So if you follow the different light rays, so suppose the this photon has, let's say, started somewhere around this lay, okay, this path, you can see this path, okay. So on the disk which I showed you, suppose that photon has started from this part of the disk, it will travel along this path, okay. Either it will, so depending on where it started, it will basically go around the black hole and then come out somewhere over here, okay. Similarly, you can try to trace the paths of different points on the disk and then trace them, okay. So they will basically come out when you see them towards us at some point on this plane, okay, so which will form an image, okay. So some paths will be basically trapped in the photon sphere, which I told you, on the circular orbit. So they will just move on the circular orbits like forever, okay. Some, after some n number of revolutions, some light rays may come out, okay. So those you would see them on a photon ring. Some paths would be like a little bit away from the photon ring, so you would see them somewhere over here, okay. So that is how the image would be created. But at the central part, okay, there would be no light coming from the central part of the black hole, which has basically gone around the black hole. That is not possible, because if it goes closer than the photon ring, then it has to fall in, right? So it will sort of create like a dark region, okay. So now let's try to look at this in terms of a simulation, okay. So now we are trying to look at light rays which do not complete one revolution, okay. So they are just being bent by the central black hole. So these are the kind of rays, and this is how they would appear on the plane, okay. So from this picture you can see that there is a dark region, and then there are the other regions around the dark center. So now these are the n equal to 1 rays, okay, which are completing, let's say, 1 or half revolution around the black hole, and then they are reaching us, okay. So they are being closer and closer to the photon ring, okay. Then we are looking at light rays which are completing 2 revolutions around the black hole. So when we see them, they will be again closer and closer to that essentially photon ring, okay, and so on, okay. So now this is everything combined, the n equal to 0, n equal to 1, and n equal to 2. So this is how basically the image will look like, okay. So let me run that image, run this video once more. So these are the rays which do not complete one revolution, okay, but which are just bended. So you can see the dark region. Now these are the rays which complete one complete revolution. So they are close to this circle, which is the photon ring, which is different than the event horizon. These are n equal to 2 rays. Also note the intensity, okay. The number of rays which were slightly bent were greater in number. So the part of the picture which is generated by n equal to 0 would be brighter. The next best intensity would be by n equal to 1. So those number of rays would be lesser compared to the n equal to 0, okay, and so on. So you would get this sharp ring-like object, okay, and then you would have the general feature. So this would correspond to the central black hole, okay. So this is basically the picture that we see, but yeah, so when we look at it from the front, okay, and if you are looking at the edge of the disk, right, so you had this central disk, and let's say you are looking at the edge on of the central disk, you see this picture, okay, if the gas is like rotating. Now what is this part? This is essentially the part of the disk which is behind the black hole, okay, but because light is bent from behind the black hole, you are actually seeing it on top. And similarly, this part of the disk is actually also behind the black hole. So you are seeing it in below, okay, because of the bending. So this is another point of view which will allow to see what is exactly happening. So if you look at it face on, okay, then this is how the image would appear. So this is completely in radio. Okay. Now obviously we are not taking a single snapshot of very less time, right? Our observations are actually going over for hours. So 5-6 hours. So it is kind of a long exposure image. Okay. So in long exposure, you will obviously see the image to be blurred. If you are doing the observation for 8 long hours, okay, because the total output of light which you see from the center, it is so less that you have to basically run the observations for very long time, okay. So when you average around what you see for 8 hours, you basically see a blurred image, okay. And then obviously due to other noise effects and other systematics in your observations, you basically see this kind of an image, okay. Now obviously it will also make a difference whether you are seeing the object along the spin direction or 90° to the spin direction, right? So this video will tell you, yeah, so there is a logo over here below which you can see the orientation of the disk, right? You can see that it is basically flipping over. So this is the disk and the central object, and if you change the orientation, you can see how the image basically changes. Okay, so it matters how you are looking at the image. Okay, so if you are looking at edge on, then you see something at the center. Now since you are also going to watch the movie Interstellar, right, you will kind of see such picture. Okay, because in Interstellar they assume that you are looking at the black hole edge on. Okay, so you will see the light coming from the black hole in this manner. So you are kind of looking at this picture. Okay, so now a little more about how that image was constructed. Okay, now since we know like what is happening in the background, let's try to understand how that image was constructed. So here I have just plotted so these are like 11 telescopes. Initially in 2018 we had only 8, but then 3 were added later. So this gives the location on the Earth. Now note that you have to observe the image at the same time. Okay, that is important. So you have to have all the telescopes on and looking at the same point in the sky at the same time, and they have to be like the data which you get, it has to be synced, right? So all these places have basically got atomic clocks, which keep time to very high accurate order, okay? And then you have to basically correlate the data because you're looking at the same object but at different places. Note that the arrival times would be different, right? There would be some time delay compared to this point because of the curvature of the Earth. So you have to keep that in mind. So what you would get is a time dependent signal, right? But then if you want to correlate it, you need to know at what point of time exactly it was taken. So all these places have very high accurate atomic clocks, okay? And then all the data which is collected over a span of let's say 8 hours of observation on multiple days, they are actually brought together at one place and they are fed into a supercomputer and then they are correlated together. Now the idea of interferometry is like you can see that our telescopes are actually quite small in comparison to the, let's say, the diameter of the Earth. But interferometry allows you to combine this data in such a way that effectively you have a telescope which is the size of the diameter of the Earth. Okay, so that basically increases your baseline. So hence you would be also seeing that this VLBI, very large baseline array, this term everywhere, right? So this basically corresponds to this technique. Okay, so imagine that if you had a very big telescope, but on that telescope you are collecting data at very small points. Okay, so that is the observation basically that we had. So we collect all the data, you feed it into a supercomputer, and then try to patch up the image. Okay, so I'll just mention that so 80 institutes basically took part along with 300 researchers which did this work and then combined this image. Now note that you don't see the Indian subcontinent from here, right? So right now we don't have a telescope, radio telescope, which looks in the 1.3 millimeter band. But in the future it will be possible like to have telescopes if we have that atomic clock which can which can be used for timekeeping, and then it can contribute. But then you also have to keep in mind that look, this is US and Indian subcontinent is somewhere at the back. So then you need to have long exposure such that by the time the Earth rotates, so you would not be looking at the same object at the same time that America is looking, right? The Earth needs to rotate and then we should come face to the center of the galaxy and then we should take the data, right? So you also need to keep in mind. So right now at 8 hours, the Indian subcontinent would barely come to face the center of the galaxy. So if you take longer exposures and if you have a 1.3 millimeter radio telescope, then perhaps India could contribute in the future to basically such observations. Okay. So yeah, so just to give you an idea of the first image which was released in 2019, right? The 2019 image was the object which was sitting in the galaxy M87. So there was also a black hole sitting at the center. Okay, so this was the first image which was released. So just to give you a feel of the comparison, the black hole there was huge. Okay, so the mass was 1,000 times more than the mass of the black hole at the center of our galaxy, and scale wise also it was bigger. Okay, so the central black hole of our Milky Way, if it can fit in Mercury's orbit, the other black hole which we observed previously, it was quite huge. So you can see that Pluto's orbit is over here. Okay, and this was the point where our Voyager 1 went. So the size of the black hole is like quite large. It is almost like 1,000 times scales larger than the black hole which we have in our galaxy. And comparatively, this black hole is also more active. So the disk around it is also more active. So there is a lot of light which basically comes around this particular black hole. So even though it is very far from us, okay, so distance wise it is basically 55 million light years away from us. So comparatively, our central black hole is like 27,000 light years away from us. Okay, but the central concept or takeaway which we can take from these two images is that the first image was basically elliptical. Okay, the first galaxy M87 was an elliptical galaxy, and the central object was a black hole. Our galaxy is a spiral galaxy, and we also have a black hole. Okay, both the black holes are essentially spinning. Okay, that was also determined by the Event Horizon Telescope. Okay, but even though these are like two different objects, okay, scale wise also and also like galaxy wise also, but the central feature which is determined by Einstein's gravity is still the same. So here Einstein's gravity is working on a different scale, and here it's a different scale, but you can see that the features are still same. Okay, so that leads us to believe that Einstein's gravity is still correct at those scales. Okay, it's like we are still getting correct results for what Einstein's gravity predicts in all possible scenarios that we are basically seeing. Okay, the other difficulty, so why was not our black hole pictured first? Okay, because it is closer, right? So why didn't the EHT telescope took a picture of that black hole first compared to the M87 black hole? So in comparison, our black hole varies a lot, okay, in the intensity. So you can see the intensity as a function of time, that it falls quite rapidly and it varies quite rapidly in just a time of hours, okay. So this is just the actual like picture from simulations, that if you just vary the time in hours, this is the variability of what you see from the central region. Okay, and remember you are trying to take a long exposure. So if you ever try to take a picture at night, okay, from let's say your camera or mobile, in long exposure, let's say of an object which is moving, then you would imagine how the long exposure would look like it would be very blurred. Okay, so imagine that you have a small child which is running around in dark and you are trying to take a long exposure picture. How would it look? You won't be able to see the features clearly, right? It would be blurred. So that is the kind of problem or difficulty we have when we try to take the image. Now, how to check like what is in the background? So what is done is you have models, okay? You have models of black holes, of masses, certain spins, certain orientations, what are the disk, what are the type of disk around it, what is the physics in the disk, etc. And then you run the simulations in a supercomputer and then you generate this kind of images, okay? So each image which you see over here is for a different configuration of the central object, okay? And then you simulate what kind of image that you see. And after you get the image, then you try to ask the question which is the best fit for the observed object, okay? And then you try to determine the parameters, okay? So this is how the simulations will look like. So this is for all different type of starting parameters, okay? Now, the best fit model which fits the data that we observe is the following, okay? So what it tells you is that, of course, there is a mass, central mass, which is like 4 million times the mass of the sun, okay? But our central black hole also has angular momentum or spin, okay? So it's also spinning, okay? And what is the orientation? So the orientation is, we are almost looking at it as top view, okay? So the object, the black hole is rotating like this, okay? And we are seeing it from top view. So that is what the picture actually corresponds to, okay? Now, interestingly, that poses another question, okay? So suppose you have this spiral galaxy and this galaxy rotates, okay? So most probably it will rotate along in this particular direction, okay? So if you have the spiral arms coming out in this way, the direction sense of the galaxy would be in this way. So it will rotate clockwise, okay? So right now we have only 2 or 3 cases in which we have found spiral galaxies which rotate the opposite way, okay? So in counterclockwise in comparison to the spiral arms, okay? So usually this is the trailing way the galaxy rotates, okay? The spiral arms are trailing. In this way, the spiral arms would be leading, okay? But nonetheless, the central object, we would imagine that it rotates in the same sense, right? In the same sense as the galaxy rotates. But like I told you, we are seeing the central object face on, right? But we are already on one of the spiral arms of the galaxy, okay? So we would have expected to see the central object actually edge on, but we see it face on. So somehow the angular momentum of the central black hole, okay, it's pointing right now somewhere in our direction, and it's in the plane, sort of plane of the galaxy. But the galaxy angular momentum, okay, the one in which it rotates, it's actually pointing perpendicular, right? So that is one of the puzzles that has also come out from this picture, okay? So this is in general what happens because of this is what we believe what happens at the center of the galaxies, okay? So I think this is where I'll stop here by just saying that what is the future, what have we learned? So it tells you a lot about the black holes. We have gone very close to the black hole, right? Very close to the event horizon of the black hole. And then it allows us to see what happens very close to the black hole about the accretion disks, okay? Whether Einstein's theory of relativity, it works to what order scales, okay? Or we need to modify it with different theories of gravity. We can check basically different theories of gravity by using such observations, etc. So in future we would be adding more and more telescopes. So hopefully the resolutions will keep on increasing. So the amount of blurriness that you see in the picture would hopefully reduce in the coming years. Okay. So I think I'll stop here and thank you for your attention. So if you have any questions, I will be happy to answer. I know that you would be all feeling very hungry.
Check. Sir, I am Ritesh.
Yeah.
I have a question that I didn't understand that time dilation. Maybe I need to understand how we define time. On Earth, we define it with respect to that transition period in the CCM 133, I think. But this is the way we define time in the space also, or is there any other way to define it?
So if you take the same clock, okay, which we are using on Earth, and if you put it, let's say, at a fixed distance from the black hole, you can see the same clock, how it basically gives you the ticking rate, right, through the transitions of the cesium atom levels. So the same clock you can put there, or the exact copy, okay, and it will work as though as it was kept on the Earth, but just the rate would be different. Okay, so it's not like there is a complete different clock you would need to measure the time there. You can use our same clock. You can in fact use your own wristwatch over there and you will get the same effect. So whatever effects, time effects are predicted by general relativity, they should hold for all clocks. No particular clock is like singled out, okay? It is like a universal theory for all type of clocks.
Okay, but I didn't understand why is that happens.
Why the rate is different?
Why the rate is different when it's closer to the black hole or massive object, or when it is away?
Right. So, see, a very simple way to understand it is to look at the frequency of electromagnetic waves, right? So, the frequency tells you about the time period between two different crests or troughs, right? So, electromagnetic wave, you have the crests and troughs, right? So, the frequency is related to that time period, inversely related. Correct? So now if you look at the frequency of photons, when you send it from, let's say, farther away from the black hole to closer to the black hole, I told you about this gain in potential energy, right? So the frequency should change. So if the frequency changes because the energy of the photon has changed when it is away to when it is close to the black hole, when it gains that potential, right? The frequency has increased. So the time period between the crests and troughs, that has also decreased, right? Because increase in frequency would correspond inversely to the decrease in time period, correct? So that time period also constitutes a clock, right? You can use it as a clock. So that is one way to understand how the rate would be small. So if the time delay has become small, it would imply that time has dilated there.
And one more thing is the bending of the space. Because we define always we define it in the 2D, but we say that it is in the 3 dimension. I couldn't imagine that how it could be.
So because, see, you would need to look at 4-dimensional images to imagine something in 3D, right? How something is bending in 3D. So we can't do that. We can only look at 3-dimensional images. So we basically just draw the 2-dimensional image. So yeah, it's not possible to draw a 4-dimensional picture, right?
We say the time sometimes for that 4 dimension.
Yeah. But when you draw that time, you are actually using one of the dimensions to draw time. So the remaining 2 perpendicular directions now are left on only 2, right?
Okay, thank you.
Okay. Any other question, guys? Anyone? Yeah.
Hi sir, my name is Amrita Ashwini. So my question is that there are a lot of theories in physics. Do astronauts and scientists believe that inside black hole there are other dimensions and neighboring galaxies there might be lives present in like that? Do scientists believe that, or they are working on it?
Okay, so there are two parts to your question. So I'll answer the first part first. So what is inside a black hole, right? So actually, general theory of relativity works also inside the black hole, except at the central point. Okay, so if you just leave the central point, the singularity, we know how GR works even very close to that singularity. Okay, so the problem is when you go to that singularity, all the mass of the star, which has basically collapsed to form that black hole, is then concentrated at that single point. So there, basically, our gravity theory, it breaks down. So then you are also looking at very small scales, right? Like a point. So then you also need to invoke quantum mechanics, because at small scales, we generally use quantum theory. So the problem is right now we don't know how to combine the principles of quantum mechanics and general theory of relativity together. Okay, so that's like an outstanding problem. So like you correctly pointed out, there are other theories like string theory. Okay, then there is loop quantum gravity, then there is non-commutative geometry. So all these theories, they somehow try to combine the principles of quantum mechanics and gravity together, and they try to describe like what is happening in the at close to the singularity or at the singularity. But right now these are just theories, so we don't have an experiment which could verify like which theory is correct. Okay, so that is one issue. So you talked about extra dimensions, right? Like for example, string theory says that it should have dimensions more than 4, right? But right now we don't have an experimental evidence that our universe is indeed so. Okay, the energy scales required to probe what is like expected from string theory, they are not like the energy scales which we have with the current technology. Okay, so right now they are just theories, they are not proven to be true. Okay, so that is the first part. Now the second part is you asked whether we believe there could be extraterrestrial life sitting in galaxies, etc. So we do have a worldwide program which is called the SETI, right? SETI, where we try to look for signals from not just from other galaxies, but even from stars in our galaxy also, right? There are other systems like which are similar to solar systems, our solar system. So we have basically found a variety of exoplanets, right? So one of the programs is to find Earth-like planets in other sun systems, stellar systems, right? So planets which are exactly in that sweet spot. So Earth is in a sweet spot where the temperature is correct. Okay, you could have like presence of water and then other features. So if we can find exoplanets, so what is exoplanet? Exoplanets are basically planets of other stellar systems which are not in our solar system. But if you look at a star in the sky, it may have its own system, right, of planets. So those planets are called as exoplanets. And if you can find exoplanets which are very similar to Earth, you could ask the question whether like similarly like life started on Earth, whether it is possible to have like life started on those planets as well. And if life started on those planets, whether the civilizations are developed yet and have the technology yet to basically send signals to us, right? So given that you have a lot number of stars in the sky, you can ask what is the probability that you could have another Earth somewhere in the universe, right? And that probability is very small, but it is finite. So there are programs like SETI which try to look at signals of extraterrestrial origin. So currently if you ask what is the answer is no. So we don't know, or we don't have a signal yet to claim that there is extraterrestrial life, but there are programs which do try to look out for it.
Any other questions, guys?
Good afternoon, sir. Sir, like, how does matter behave inside the black hole and outside the black hole, and what is the difference in their behavior?
Okay, so outside the black hole, matter would follow trajectories, okay, orbits. Just like planets follow orbits around the sun, the matter outside the black hole will also follow orbits, but those orbits are determined by Einstein's theory of gravity. So they will no longer be like ellipses, okay? There could be some distortion from ellipses, okay? Or if you have something like large amount of matter, they could be sitting on disks, okay? So I showed you this picture. So this picture. So you could have, is it possible to share my screen? Yeah. So this is the black hole. You could have a lot of amount of gas. Okay, so there could be like other stars around the black hole. Let's say if a star, if it eventually captured by the black hole through its gravity would first rip off the gas outside of the star. So that gas would be basically spiraling inside into the black hole. So that picture may look something like this. So every particle over here would be following some trajectory, okay, some orbits, but that orbits could be dissipated because of friction, okay. Those particles can go hit each other, have influence on each other, so they could dissipate energy. So overall they would be spiraling and falling into the black hole, okay. Now once inside the event horizon of the black hole, matter has to go and hit the singularity, okay. That is compulsory. That is given to us by, again, Einstein's theory of gravity, okay. So they have to go and ultimately hit the singularity. So all matter that crosses the event horizon will eventually go and hit the central point of the black hole, which is the singularity.
Sir, and how does matter behave in the center? In the central
You mean
hole?
at the singularity?
Yes, sir.
That we don't know, because gravity theory, it basically breaks down at the singularity.
Sir, is there any difference between the matter by how it behaves outside of the black hole and inside the central horizon of the black hole?
Inside the event horizon?
Yes, sir.
So inside the event horizon, it will behave similar to what it did outside, okay, but not at this, except at the singularity, it would be kind of similar. So the same sort of equations apply even inside the event horizon. In fact, there is this curious thing that suppose if you are falling into the black hole, you may not even know when you have crossed the event horizon. So life is as normal. So let's say if you are inside a rocket, outside the black hole, if you are sitting inside the rocket, you can obviously feel the force of gravity, but let's say if you are freely falling, okay, if you are just freely falling under the influence of gravity. By freely falling, I mean, suppose let's say if you go to above the surface of the earth, and let's say if you are inside a cabin or a lift, okay, and if you just leave that lift, okay, and let the lift fall under the influence of gravity, and you are inside that lift, so you will be freely falling, you will feel like weightless inside, okay. And let's say now you are in the same rocket or the same lift which is outside the black hole, okay, and it is just freely falling towards the black hole. So within that lift, you will be feeling the same effect of weightlessness. You will cross the event horizon. You will, if you are not looking outside, within that lift, you will not even realize that you have crossed the event horizon. So it is as same as what it was outside in a freely falling frame, okay. But things will start to behave in a different way when you go close and close. Then there will be something which are known as like tidal effects, okay. Due to tidal effects, what will happen is so if you are, let's say, falling feet first into the black hole, so your head is out and your feet is inside, okay. Due to the tidal effects, you will become stretched and stretched, okay. So there will be difference in the falling. So your feet will go away and away compared to your head. So there will be a stretching effect along the height, and there will be a squeezing effect, okay, along the width. So you will become like narrower in this direction, but longer along in this direction, okay. So those are due to the tidal effects of the black hole.
Is there any other questions? Anyone? Yeah.
Just curious, how many types of redshifts are there? Doppler shift, gravitational redshift. So all of them are same, or
No.
they should be same?
So like you said, there are three. So one is the usual Doppler effect, right, which is due to relative motion,
Right.
right, due to the relative velocity. The other is the one which I mentioned. So this is the gravitational redshift. Okay, this is just due to the presence of gravity or curvature which is causing the redshift. And there is another one which is the cosmological redshift. So we know that our universe is basically expanding. So any photon which was emitted, let's say many distance and many years away, by the time it has reached us, it is basically redshifted. So that's the cosmological type of redshift.
So all the three, nature of all the three is different.
So the derivation is kind of different. Many people, they try to relate the Doppler redshift with the cosmological redshift, because they try to understand that if there are two galaxies which are like receding away, then if you try to use the Doppler shift formula directly, then they try to compute the cosmological redshift. But then you can even have redshifts which are greater than 1. So if you try to do that, you will find that the receding velocity of the galaxy is faster than the speed of light. Right, but that can't happen. You cannot have something which moves actually faster than the speed of light. Okay, so in the cosmological redshift, what happens is there is due to gravity, there is one scale factor. Okay, it defines how we basically define distance between two objects. That scale changes because of the expansion. Okay, that's a gravity effect. So which is quite different than something which is moving away. It looks like it's moving away, so that's like an apparent effect. But cosmological redshift is not that. It's because the scales are basically changing. Okay.
Next student of National College Jayanagar. Out of curiosity, I would like to know if time travel has been examined in the black hole.
Okay. So for time travel, basically what you need is what you need is basically closed curves. So I had mentioned about these world lines, right? Any object in the universe will have a world line. World line meaning at a particular time it will be described by some position. So it is that world line is basically drawn in 4-dimensional space-time, right? To have time travel, this world line needs to again go back and then connect with your world line at a previous time. That would mean that you have time travel, right? That's like traveling back into the past. So to have such curves, you need to have very special curvature, okay? So those solutions as of now, we don't know from Einstein's equations, okay? So Einstein's equations do not give us such curvatures which will loop back the world timeline of a particle back to itself. So then traveling into past is not possible. At least those solutions are not known. So people talk about what are known as like wormholes. Okay, they try to connect different part of the universe, okay, through wormholes. But if you want to create a wormhole in our universe, the matter and energy distribution should be in such a way that it somehow kind of violates like quantum mechanics. Something got violates. Okay, so right now we do not have like known solutions which would create those loops of world lines. So yeah, it's just a concept as of now, but we don't have an actual solution which would work in our universe. Yeah.
If there are no further questions, I would request Altaf sir to deliver the thanking note and give out certificates of our previous workshop.
Thank you. First of all, a huge round of applause for such a beautiful presentation and such a beautiful lecture to Dr. Sanved Kolekar. Sir, thank you for being here with us despite the short notice. I remember I just emailed him and he wrote back immediately on the same day and agreed for interacting with us. We would like to have more and more conversations with you. We are planning to have an astronomy lecture series in the coming month, and we would like to bring in, stalwarts like you all in the subject, and we would have much deeper and better understanding of cosmology, and we will also try to do some activities through B.V. Jagdish Science Center. Now, I think this is a great moment for giving out prizes for our previous workshop. Our previous workshop was a workshop on science journalism. We wanted to identify and train peoples who are willing to become science communicators from different backgrounds. They may be from journalism, from arts or commerce or science. We wanted to identify people who are trying to look out for careers in doing journalism of science. And we have received their certificates just yesterday, and we would like to hand it over to the participants, the prize winners, through you, if you're okay with that. Ms. Chinmay, I would like to call upon Ms. Chinmay to read out the names of prize winners. It will take 5 minutes. Chinmay.
First prize goes to team Jyoti Nivas College, Amrita Krishna Kumar Reddy and Jennifer Sheriff Daniel.
Are you here? Is she here? No?
And the fourth prize goes to BMS College for Women, Sanjeevi B and Shivani. And the fourth prize goes to team Bangalore University, Harini. Vijaya College, Jayanagar, Nitin. Manoj, Satya, Emmanuel.
These are participation certificates, huh?
Yeah.
Okay. ಇನ್ನು ಯಾರಿದ್ದಾರೆ? ವಿಜಯ ಕಾಲೇಜ್ ಅಷ್ಟೇನಾ? ಅಷ್ಟೇ. ಥ್ಯಾಂಕ್ ಯು ಅಂತ ಹೇಳಿ ಮುಗಿಸ್ಬೋದು.
Participants from Vijaya College, Sahana BM, Lekha Vidya. Thank you.
Yeah, thank you, Chinmay. I think with this we will break for lunch, and just after 30 minutes we will start a movie. The movie is Christopher Nolan's movie, Interstellar. It's a great tale said about. Okay, I already see a lot of hands raised. We'll start after 30 minutes. What's the time now? It's 1:35. We will start at 2:10. Okay, have your lunch and come back. Thank you so much. And there are some refreshments outside for you.
As a business, you want to make your customers feel special with great customer service. But managing support through email can slow you down. That's why we created Hiver, a delightfully simple solution for your customer service needs. You get all the functionalities of a powerful help desk right inside Gmail. So no more missed emails, no more asking around for updates, no more confusion. With Hiver, your team can work together on emails using tools like email assignment, chat-style notes, collision alerts, and shared drafts. And when those email volumes hit the roof, Hiver's powerful round-robin assignment, automations, and SLAs keep your team's workflows streamlined. Not to forget, you can track all your important metrics with Hiver's rich analytics. And all of this through the super familiar interface of Gmail. Sounds too good to be true? Don't take our word for it. Visit hiverhq.com and get yourself a 14-day free trial. Hiver, the world's first help desk built for Google Workspace.
Scrolling your time away, comparing furniture on e-commerce platforms, and not sure if you will get what you see? We make furniture for the digital age. This lets us replace awful industry practices like overpricing in showrooms. No worries. Our 2.5-acre factory with the latest computer-controlled machinery and our fulfillment centers across Bangalore, Chennai, Delhi, Hyderabad and Mumbai, we are with you always for any after-sales support. We believe quality should be affordable. The furniture that we showcase to you is based on over 25 years of experience. You'll